All right, y'all. Happy Monday. Such a Monday. Okay. So we've got on the board what we pretty much ended with on Friday, because Friday comes before Monday. We were doing the constructing an MO diagram for H2, which is our simplest molecule, so it's the best place to start. We have a 6-step process. Step 1, draw the compound. Step 2, count the number of valence electrons. If you switch the order of 1 and 2, you're going to be fine. Like usually you have to count how many valence electrons you have before you draw the Lewis structure, so follow your heart. Number 3, do any of the atoms in your molecule need to be hybridized? Do they have shapes that require hybridization? If we're doing H2, that answer is no. 4a, so number 4, which has got 4 parts, is construct the MO diagram, so like do the actual work. 4a is just get all of your stuff set up, right? So we have what are the atoms that are part of our molecule, right? So the atoms are going to be on the outside, the molecule is going to be on the inside, so that's 4a. 4b is then setting up the energy of those atomic orbitals, right? So how do the atomic orbitals relate to each other? In this case, we have 1s of H compared to 1s of H. Those should be the exact same, and they are. And then step C, mix to get MOs. That's the tougher part. That's where we're actually starting to do the new tasks. In general, you mix so that you end up with enough new molecular orbitals to match the number of electron domains that you have. Right? In this particular case, we have 1 electron domain. It's between the hydrogens, so we had to mix to make sure that we got this new electron domain. In doing so, we mixed 2 atomic orbitals, so we had to do that constructively and destructively. Every time you mix things together, you have to end up with the same number of orbitals as you started with. Step 4D is then labeling your molecular orbitals. Right? Let me go back to 4C. Let's get some more words on here. Number of electron domains. Constructively, destructively. So our orbitals overlapped constructively. Constructive interference. You can think of that as overlap, right? Orbital overlap. So it's constructive interference that gave us a bonding interaction. And therefore a bonding MO. If we're going to do that, we also have to do this destructively. Right? You're not allowed to destroy energy from the universe. Right? You can only change its form. So if we do constructive interference, we also have to do destructive interference. Or overlap. This is giving us an anti-bonding interaction. And the way that we denote anti-bonding is with an asterisk. Right, we use asterisk to say anti-bonding. All right, step 4 is then labeling. Right, so and by labeling we mean sigma versus pi versus neither of those. So this new interaction that we have, did we bring them together and the orbitals overlapped along the internuclear axis, that's your sigma? Did they overlap above and below the internuclear axis, that's pi? So in this case, we brought them together. We increased overlap along the internuclear axis, so it's definitely a sigma type MO. Right, and then you say, what were the 2 atoms that were involved in this MO? So in this case, it's sigma HH. Right, that's our lower energy new MO. Then we go to the higher one. And again, you start, where is that new overlap? It's still along the internuclear axis. That's how we brought the orbitals together. They happen to cancel each other, so it's still sigma. But it's anti-bonding, which is where that star comes in, or the asterisk. I call it sigma star. And so the star is telling you it's anti-bonding, and it's between the 2 H's. So this picture here with the white circle, the red line, and the yellow circle, that is the sigma star antibonding orbital. That whole thing is the orbital. right? It's not just part of it, it's the whole damn thing. All right? So that's the thing that y'all really need to be on board with. Okay, so that's labeling. Adding electrons. How many electrons in the valence orbitals did we have? How many electrons do we have to use right now? 2. Cool. Where do you put them? At the bottom, right? The same way that you add electrons to any other energy diagram. You go low to high. If you have degenerate orbitals, you split them up before you pair them. When you pair them, you give them opposite spins. We haven't been talking about electron spin because it doesn't have a macro level effect. We can't see whether it's positive spin or negative spin, so I haven't been talking about it. So if we add our electrons, we have 2 electrons that go into the lowest possible molecular orbitals. All right, so the other thing to pay attention to is that now we're only looking at the middle. We're looking at that MO diagram. We now effectively ignore the atomic orbitals because we used them up. Right? We used them to make these new molecular ones. So if I had 4 electrons, right, if instead of 2 I had 4, I wouldn't put 1 in each of these because those aren't part of the molecule anymore. I would have to put 2 up here. All right? So for homework, show MO diagram for the molecule H2 minus. Yeah.
Do you have to put the box around it?
No. You don't have to put that big old yellow box. That's just me cluing you in, like, this is the new stuff, this is the part we're dealing with. So lastly, part 6 is the frontier molecular orbitals. This is where we're looking at our new molecular orbital diagram, saying what are, which orbitals are easiest to interact with, right? Which ones are most accessible energetically. And what we're talking about is in terms of these electrons. Right, for H2, it's pretty simple. We've got 2 frontier molecular orbitals, highest occupied and lowest unoccupied. Those are always your frontier molecular orbitals. Right, so you look at, of all of my molecular orbitals with electrons occupied, which of those orbitals is highest in energy? Right, so what is our highest occupied molecular orbital for H2? Highest occupied, sigma or sigma star? I need that with way more gusto from everybody. What is the highest occupied? Sigma. I feel like the same number of people said it, just louder, but I'm here for it. All right, so here's our highest occupied molecular orbital. All right, and then by occupied, we just mean has electrons. Of your new MOs, which ones have electrons occupied? Highest is of the ones with electrons, highest in energy, which then means your sigma star. Sure. This is your lowest unoccupied molecular orbital. Of all of the molecular orbitals that you have that don't have electrons in them, which is the lowest. Right, so every time we're talking about these frontier molecular orbitals, your FMOs, they're going to be 2 molecular orbitals next to each other in energy. Right, they're somewhere in the middle of your MO diagram. The reason we care about them is that's where the valence electrons are, right? These would be the highest energy valence electrons, the ones available to do work. This is your lowest energy empty orbital, right? If we're going to interact with that molecule, we've got to put electrons into it. Right? If we're putting electrons into it, those electrons need to go somewhere. Sigma star is a pretty good spot. All right, so that's why we're focusing on the frontier molecular orbitals. Okay, thoughts, concerns about this? What we just talked about, which was a review of Friday. Yeah.
When you say that if you were to add new electrons,
Uh-huh.
then go into the sigma star
Mm-hmm.
MO, how does that work? Like, would that be considered like the 2s?
Mm-mm.
So then, we were just talking about like 1s.
No, now we have sigma and sigma star. Like, we no longer have the 1s and the 2s. We've made a molecule that has its own new MOs, which is why we left the 1s's behind. They're outside of our box. And so the things that, how many of y'all had discussion today? Okay, so you probably learned about bond order. A Blank stares of doom and destruction sounds great. You learned about bond order in today's discussion, which has to do with how many electrons do you have in bonding orbitals versus anti-bonding orbitals. So H2 minus, I'd be interested to know what you think that bond order is going to be. If you haven't seen it yet, don't worry about it. I'll get to it by Wednesday. All right, so again, any thoughts, concerns about this diagram and the steps we took to make it? All right. So one thing that, oh yeah, what's up? Yeah, so these two are the frontier. Highest occupied and lowest unoccupied are both frontier molecular orbitals. They're at the frontier of reactivity. Okay. So let's check out this red dotted line and try and get a little bit more understanding of it. All right, so that red dotted line is our node. And there are some things that we need to know about nodes. All right. It's telling us that there's no electron density. That is true, is what the node is telling you. The other thing to understand is that in an orbital, every time you pass through a node, you change phase. Pass through a node, phase changes. Right, and to really understand that, you have to go back to where did this picture of the orbital come from. Right, so the picture of the orbital is coming from our wave. Let's say this is the p orbital wave. Okay. Here, it's our nucleus. And in this wave, we have above and below the reference line, whatever that reference line means. Right, so above and below. The way that we're going to think about it is unfilled in and filled in. Right, to get any physical understanding of what that wave means, we have to square it to say what is the positional probability of an electron in relation to that particular nucleus. Right, so we square the wave, square the function to get probability function. Right, so there's our nucleus. Our minuses become positive. Okay, and the thing that you know is true when you multiply something negative by itself, that number becomes positive. Right, but what we're doing is in our head. Right, like we are making that probabilistic function. We are doing that. The wave isn't doing that. And so what we need to do is remember where that probability came from. And so that probability came from a negative phasing. All right, so then if we do our 3D magic, right, take that reference line, spin it like a stick, spin, 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 you get that 3D shape. And we pass through a node, we get a different phase. We pass through a node, we get a different phase. You pass through a node, you get a different phase. Right, so every time you go through a node, your phase changes. And that comes from the node in a wave. Right, so looking at it as a p orbital, you're like, but what node are we talking about? Why is there a plus or a minus? It comes from this original wave. Right, so that's why we get the shading that we do. Also, the phasing doesn't mean anything physically. Right? It's not like the good phase and the bad phase. They're just phases. Yeah, like one isn't inherent for anti-bonding and the other one for bonding. It's not a thing. If you look at the pictures that I drew for bonding, anytime two of the same phase come together, you're increasing density between the two atoms, bonding. Right? Whether you color it in or not is up to you. I will color in the smallest amount possible to save my lungs from inhaling a whole crap ton of chalk. That's the only reason that the smallest amount of things get colored in. That's it. So if you're looking at it like, but why did you do that? Just remember, oh yeah, because Pete's lazy and he cares about his lungs. Okay? It's arbitrary. The phasing is arbitrary as long as you follow the rules. Every time you go through a node, you switch that phase. Did that answer your question that you were about to ask? Kinda? Ish? Okay. You still have it? You're fine? Okay.
When you say it's arbitrary, then like you don't even think about what information.
Yeah. It is thoroughly arbitrary. Like 100% arbitrary. And all we're really doing is saying, does the same line up with the same of something else? That's all we're using it for. Yeah.
Like physically, what makes one phase different from another?
Nothing. There is physically no difference of the phasing. Truth? Truth. Yeah, like this is a mathematical, like a math answer. That's either a positive number or a negative number that has no bearing on reality, which is just awesome to think about. There's probably like quantum things that matter. This being Gen Chem, we're not going to dig too much deeper into that. I'm already towing the line with quantum chemistry by going over what I'm going over. Okay. Yes? What does it mean to go through a node? It's like going through a car wash. No, I have no idea. Mainly in a wave, every time you cross over the reference line, you're going through a node. Or this is generating the node. Because when we do the probabilistic function, you're like, oh, hey, this went from a wave, which means maybe something, to how likely is it to be to the right or left of this point? And at this point, I have zero likeliness of being there, which means I'm at a node. So like the meaning comes from here, and then this came from our wave shape. Okay. All right. So mainly, as you're going left to right, every time you get zero electron density, you then switch your phase. Sometimes it's the nucleus. Like for a p orbital, the node is at the nucleus. At the end of lecture today, I hope I can get to it, we're going to look at a sigma CH bond, and we'll see like where are the nodes, where aren't the nodes. Cool. All right. So today, this was HH, the simplest of molecules. All other molecules tend to be a lot more complicated than that. How many of y'all remember doing MOs in high school? Like diatomic molecular orbitals? Like N2, O2. No is the better answer. I am happy that you don't remember that or that you didn't do that, because it means you have less to unlearn. And by unlearn, I mean that is the correct way that you may have learned in high school. This is going to be our fake way that works all the time. All right? So what we're going to do today, is a mixture of two types of theory. Notice I'm not writing that on the board. I just want to be clear with you and not lie to you. So there's two main types of theory. There's valence bond theory, which says, hey, here's a bond. What atomic orbitals went into making this particular bond? That's valence bond theory. Then there's MO theory, molecular orbital theory, that says, here's a molecule. How did all of these different atoms mesh together to make that? Slightly different. It's more holistic and less individual. And so what we're doing is saying we're going to look at each of these individual bonds and say that if we add all those up, we get the molecule. Right? Which makes sense. Right? A molecule is made up of a bunch of bonds, so let's just do that. There's issues there. Right? There are issues there. It's not very true. Like on a mathematical sense, that's just not how the things work or look. But it's easy to do. So what you're going to see by the end of this is if you can draw a Lewis structure, you can construct an MO diagram. So let's go with that. If you can draw the picture, you can make a more complicated looking picture. Right? It's all circularly related, which is why we're doing it. And what we can do with that is then make a whole bunch of predictions. We can predict, hey, which bond should break more easily based on spectroscopy? Or, hey, if this interacts with that, like which of these electrons are most reactive? Which of those empty orbitals is probably going to get interacted with? Like which of those is easiest to fill? Right, so we can use the frontier molecular orbital theory to predict reactivity pretty well. And by pretty well, I mean like 90, 95% of the time it's going to work. Right, and that's by using two very different theories and just smashing them together like children. Like just straight up Yeah, that works. Right, like square peg, circle hole, we're going for it. And it's going to work fairly well. We're just going to shave off the edges of that square. All right, so let's handle this. What we're going to talk about today, hybridization. All right, so this is back to Unit 1. So some things that you hopefully remember is that hybridization exists. We have VS-EPR theory that says based on the shape of the molecule that I drew, the central atom has a given hybridization. And that's what we're going to roll with today. And we're going to assume, and we're doing this assumption, if an atom is in a molecule, it is hybridized. Right? And again, that's a total fake thing. Hybridization is not real, but we're using it because it's easy to deal with. It's very easy to predict it if you just assume it's there. Right? So again, we are simplifying like MFs to make sure that it's doable via art pictures. Okay, hybridization review. We're going to start with the simplest one, SP. Right, so SP hybridization, if you have a central atom and that atom is SP, what shape do you get? A line, linear. Right? If that central atom is SP, we're talking about linear. Okay, so the way that we're going to hit this up, let me give you some coordinate axes real quick. We got X, Y, and Z. All of our pictures are going to follow those particular axes, X, Y, and Z. So linear. What we're going to do is take two of the atomic orbitals and hybridize them to make new hybridized orbitals. So we're going to take S and PX. Why PX? Because I tend to draw things left to right. You use whichever orbital fits the picture that you drew. Again, arbitrary, up to you as long as it's consistent. The math is going to end up being the same. The picture is going to end up being the same, just different orientations. So S plus PX. So here's our central nucleus. There's my S. Here's my PX. I'm going to arbitrarily color in the right. If you want, you can color in the left. If you want, you can color in the S. You follow your heart. Minimizing chalk intake to live longer. So S plus PX. Those are the things that we're hybridizing. All right, and we're going to do this. We're going to hybridize. And we're going to get two SP orbitals. We started with two atomic orbitals. We have to end with two hybrid atomic orbitals. And the way we're going to do it is S plus PX and S plus the negative of PX. And so S plus PX is as it's drawn. It's going to give you central nucleus, S plus the negative. Okay. So S plus PX looks like this. So I'm going to get big on the left, tiny on the right. Right, every time you're going through 0, we can't actually have anything there. Right? That's like a non-starter. If there is a node in any of those orbitals, that node carries through to the hybrid orbital. Now if I do that down here, right, if I do S minus PX, what should that look like? I try not to describe it perfectly, try and describe it in relation to the first one I drew. Yeah. Yeah, a mirror image of the first one. Just flip it over. So I'm going to get my small side on the left and my big side on the right. So what we've done is we've created an increased amount of electron density pointing towards the electron domains of a linear atom. Yeah? I have something to the left, something to the right. Why do I have that? Because that's what we've got here. All right, so this creates SP left. This creates SP right. Right, they're both SP hybridized orbitals. One has more density to the left, one has more density to the right, giving us the shape of the molecule that we're hoping for. All right, checks out. Now, the energy of this. SP. So here's our atomic orbitals, and here's an atom's atomic orbitals, and now a hybridized atom's atomic orbitals. So an sp hybridized atom's atomic orbitals. So the atom started in a way, we hybridized, we got something different. So it started some kind of way, then we took the S, and we took one of the P's. We mixed them together, we added and subtracted them from each other, and we got two new things. How should the energies of sp left and sp right relate to each other? Right, what is the chemistry term for how those energies are related? 4 syllables. Degenerate. Nailed it. Sounds like 4 syllables. No charades. Y'all ain't into F all y'all. You need to play more party games. All right? So degenerate. SP left is the same energy as SP right. How do the SPs correspond to the S energy level? Higher or lower? Higher. Right? We took some P, mixed it with S. That should raise the energy of the S. If you think about it the other way, if I take some S, mix it with the P, I should lower the energy of the P. Right? So we're in between S and P with this new hybrid orbital. There's my SPs. All right, so just like in our atomic or our MO diagram, I use dotted lines just to say, hey, so I took these two things, brought them together, they end up here. All right, so that is the sp hybridized atom's atomic orbitals. So what other atomic orbitals does that sp hybridized atom need to have? Right, those other two p orbitals. Right, we started with 4 atomic orbitals. We have to end with 4 atomic orbitals. We mixed 2 of them to make hybridized atomic orbitals, but the other 2 don't disappear. So just don't forget your unhybridized atomic orbitals. They are still there. Right, so that's how you conceptualize getting left and right for an atom. Okay. What we're going to go through next, SP2 and then SP3. SP actually gives us the chance to say, hey, how are we mathematically getting these hybrid orbitals? SP2 and SP3 a little too complicated. The reason it's complicated is because the contributions aren't 50-50. All right, so if we look at SP2, we get trigonal planar. We're going to take 3 atomic orbitals to get 3 hybrid atomic orbitals. So let's say S, PX, and PY become 3 SP2s. So I'm using X and Y to make it easier for me to draw this picture that I'm about to draw for you. Normally, as you're familiar, when we're doing trigonal planar, I prefer the XZ plane. It's easier to see, it's easier to deal with. But for right now, I'm going to be good to us. So S, PX, and PY. S, PX, PY. Oh, sorry, I've been using yellow. There we go. Yellow. S, PX, and PY. Now, it's not 1-to-1-to-1 in each of these 3 things. Right? It's not like S plus PX minus PY. It's a little funkier. Right? We've got different contributions. Because of that, I'm not going to go into it. But we do know what the answer looks like. Let's see. Got some of this. We've got some of this. And we've got some of this. Got that plus that plus that. Now, if you recenter those on the same nucleus, right, overlay it on the nucleus, you get your trigonal planar shape, right, where your larger electron density for that orbital is pointing towards your electron domains. Larger lobe of each hybrid orbital points toward electron domain. And that is from VSEPR theory. You already know where the shape is. Now I'm just trying to give you a reason to understand why we do it that way. All right. So that's what that shape looks like. And then if we get our energy, we have S and P. We hybridize. We take S. We take 2 of the P's. This P does nothing. Bam. All right, PZ stays where it was. And now we get 3 new SP2 hybridized orbitals. They all have the same shape, but different orientations. Therefore, they're going to be degenerate to each other. SP2. Where are they? Somewhere in between S and P. All right, notice that this is different from what we were doing with mixing atomic orbitals to make molecular orbitals, right? So those have 2 different nuclei that are then somehow meeting in the middle. Here, everything is still on that same nucleus, right? So our energies keep ending up being the same. Right? So it feels similar, but is in fact different. So here's our hybrid SP2 hybridized atom atomic orbitals. 3 SP2s, and above that, a P. All right, and then last, we've got our SP3 hybridized orbitals. That's tetrahedral. We're going to take all of those atomic orbitals, mix them all together in 4 different ways to get our 4 different electron domains. I'm going to draw them all on this one nucleus because why not? Then we're going to fill in a whole bunch of spots. Yeah. You may be looking at that saying, but that's so gross. To which I say, yeah, it is. So we're going to do that. And we're going to get 4 SP3 hybridized orbitals. And the big lobes are going to be pointing in the directions of your tetrahedron. All right, so here's your 2 that are in the plane of the paper. And we get 1 coming out and 1 going back. And our little lobes are all going to be shaded in. There's one back there somewhere. And again, why am I shading in the little lobes? Because I'm lazy. If you want, shade in the big one. Follow your heart. If you want, shade in some of the big ones and some of the small ones. Whatever. As long as every time you go through a node, you switch your phasing. All right, so there's our SP3 hybridized looking thing. Again, big lobes pointing towards the electron domains. Now we take our S orbital, all 3 of those P orbitals, and we're going to hybridize them. Believe it or not, we're going to get 4 degenerate SP3 hybridized orbitals in the end. Fancy. All right, so here's our atomic orbitals. And then an SP3 hybridized atoms atomic orbitals. Different. 1, 2, 3, 4 SP3 hybridized orbitals. All right, so the next thing I'm going to have you all do is then compare the energy of each of these hybridized orbitals to each other. Right, so for different hybridizations of carbon, I want to know the energy of SP is greater than, equal to, less than the energy of SP2 is greater than, equal to, less than the energy of SP3. All right, rank those energies all for the same type of atom. All right, so the carbon S and P orbitals all started at the same point. You then hybridize them to different amounts. How do those different hybridizations affect the energy? Chat about it. So I forgot how to count to 4. I thought 4 and wrote 3 because I'm a legend. So there should be 4 SP3 orbitals that you're making, not 3. 4 instead of 3. All right, how are these energies? So SP versus SP2 lean to the one that's bigger. SP or SP2, which one is higher in energy? SP or SP2 lean to the one that's higher in energy. SP or SP2 lean to the one that's higher in energy. Most people are giving me SP2 vibes. I'm loving it. All right, if you're thinking that, then you should also be thinking this. If you weren't, then you were guessing for one and thinking like, maybe I'm wrong, and you just guessed the other one for the other, so you'll be right at least half the time. Good test-taking strategy, bad for learning, but I appreciate you. All right, right? SP3 has more of the higher energy p orbital in each of those hybrids, so it should be overall higher in energy. Yeah? Sound good? Sort of like our isotopes, right? Your weighted average. We have more of the higher energy thing in each of these averaged orbitals. Should be higher in energy overall. All right, we're going to end this little chat with our 3D templates, which is again a review. So this is lecture 7 or 8 throwback. I'm throwing it way back, 30 lectures ago. We had these templates. Here's our central atom. So with these 3D templates, we're using lines point toward electron domains. And the lines are the hybrid atomic orbitals. All right, so if we just put in where are the hybrid orbitals pointing for SP, if we're talking about our linear in the x-axis, then we got those. SP2, I'm going to go back to my xz plane because I like it best. If we're at SP3, we have all 4 are hybridized. And then what we do is that any non-hybridized atomic orbitals are explicitly drawn. They're not shortcutted in any kind of way. They're just drawn. So for SP, we have our PY and our PZ. For SP2, we've got our PY. And so really the only thing that's new here is I'm adding that phasing. I'm adding the shading to match what we've talked about with waves and orbitals. So this should look the exact same. All right. I think I can actually finish today. So excited. Let's do this. Let's go. All right, I guess before I do that, thoughts about hybridization? Like, I got to be fair. Thoughts on hybridization? Yeah.
The thing we did with SP, where we did both S plus PX and S plus minus PX.
Yeah.
Why didn't we do that for the other two?
Got it. So why didn't we do like a simple linear combination, like this plus this and this minus that? The contributions are different. So it's not just like S plus PX plus PY divided by 3. It's like some amount of S times a different amount of Y plus a different amount of X to get those 3 different shapes. And then for SP3, it's even more complicated than that. So you really have to mix and match to get the directions that we see. Okay, yes? One sec. Let me just get closer to you. I'm behind a fan. Yes?
Can you explain again why the energy of SP3 hybridization is higher than others?
Cool. Why is SP3 higher than the others? Yeah. So remember in isotopes when we had a whole bunch of different atomic weights, and then we averaged those out based on how contributive they are? Yeah? So this is like we have 25% S and 75% P versus 50% S, 50% P. And so if you take the energy of S and the energy of P and then use the percentages, then you get different values. And so since SP3 has more contribution from the higher energy thing, its average is just a higher value. That work out? Okay. All right, so let's hit up the MO diagram for SP3. SP3, what? Construct MO diagram for CH4. That one just, the words wouldn't leave my mouth. All right. So step 1, draw that thing. I got my carbon, got my H, I've got an H, I've got yet another H with still more H. Notice that I drew that in 3D. You should do that too. You know what it should look like, so don't rely on those 90-degree angles which you know are wrong. From now on, draw everything in 3D. It doesn't take that much longer and will help you. Hot take. Number 2, how many valence electrons are there? Quick, fast. How many valence electrons? Don't look over there. How many valence electrons? 8. How do you know? You got 4 bonds. 4 bonds. 2 in each bond, that's 8. Right? We're being quick with it. So don't rely on trying to count from the periodic table. Just think, oh, hey, I know what that picture looks like. It's going to give me 8 valence electrons. All right, and then third, of the atoms in this molecule, are any of them hybridized? Of the atoms in this molecule, are any of them hybridized? Notice that I drew it as a shape. Hey, yeah, that middle one is tetrahedral, so its hybridization is going to be SP3. So carbon is SP3 because 4 electron domains. Again, back to lecture 7 or 8. Okay, now let's go through the work. 4A. Let's set up this new MO diagram construction. Now in this, it's a little bit different. The middle is still the middle. Right? So we've got our molecule in the center. So that's our CH4. But what do we put to the left and to the right? Okay, the way that I usually set this up is on the left side, I have whatever the central atom is. Right, so here's our central atom. In this case, that's carbon. And we know that carbon is hybridized SP3. So let's remember that. And then on the other side, on the right side of our molecule, we're going to have our peripheral atoms. Peripherals. Which is going to be 4 hydrogens. Right, so 4A is just saying, what are the atoms that I'm using? How am I going to split up my work? 4B is now a little more complicated. 4B is saying, how do our energies relate to each other? Okay. So, for different atoms, you're going to have different energies, necessarily. What data would you look at to get this information? Like what scientific data gives you atomic orbital energies of the valence electrons? Get back to Unit 1. Ionization energy. Right? Ionization energy says, hey, I put in this much energy before that electron pieced out. Yeah? So that's giving you quantitative numbers for that. And we know that all of our different atoms have different values for all those things. We then sort of guess based on whatever the ionization energy is, saying, well, I hybridized it, so a little bit above, a little bit below, but probably somewhere in the middle. Right? We can get close. When you have different atoms, we're going to have to make some like house rules. Yeah? You cool with house rules? I mean, you have to be. They're already all house rules anyway. We got 6 house rules. What's like a couple more? So for different atoms, the things that matter. Electronegativity affects AO energy and energy level affects AO energy. Energy. Okay? Energy level, I think you can understand pretty well. Right? Up or down, you're like, yeah, the lower the energy level, the lower the energy should be. Right? 1 should be lower than 2. The caveat to that is that electronegativity does matter. All right? So more electronegative, how should that affect the atomic orbital energy? So if we're looking at F versus C, fluorine versus carbon, which has the lower atomic orbital energy? Fluorine versus carbon, which is lower? Which ionization energy is higher? Fluorine or carbon? Why is the fluorine ionization energy higher? It's more electronegative. A, right? So that means it is lower in energy. The higher your electronegativity, the lower your atomic orbital energies are going to be. Right? And so what we have to figure out together is which one do we consider first? Right? Which one are we going to consider first? What do you want to do? Good talk. We'll do electronegativity first. How's that? We'll go by electronegativity, and then if they're the same, as is the case here, we'll look at energy level. Right? So in this case, we'll say this is first and then second. So we'll mainly base our atomic orbitals energies on electronegativity. All right, so carbon SP3, 1, 2, 3, 4. SP3 hybridized atomic orbitals. Where is H going to be in relation to that? Based on electronegativity, where should the hydrogen orbitals be? Same. Are their energy levels the same, though? No. So should hydrogen be a little higher or lower? Should hydrogen be higher or lower than carbon? A little bit lower, right? If the main thing is electronegativity, then we're like, all right, it's probably close to here, but it's a lower energy level, so let's go a little bit below. All right, so lower, because same electronegativity, but lower energy level. All right, so that's the new thing that we're seeing today for 4B. Right, how do we really evaluate the energies of different atoms? All right, and then 4C. We got to mix. Okay, and then how are we going to mix them? All right, we need to mix these so that we're putting electron density where the electron domains are. All right, so mix AOs to get your necessary, not an accessory, mix atomic orbitals to get necessary electron domains. All right, so we're going to take our SP3 hybrid C, we're going to take one of our H1S's, and we're going to smoosh together to get the electron density between the carbons and the hydrogens. 1, 2, 3, 4. And what these are going to look like, here's my carbon, here's my hydrogen. It's going to look like that. I've increased the electron density between the carbon and the hydrogen by mixing the SP3 with the H1S. There's your sigma CH. All right, what I want you all to do is finish that. All right, what should the anti-bonding look like? Where are the electrons going to go? What is your highest occupied? What is your lowest unoccupied? All right, and then on Wednesday, we'll keep working with this. All right, much love. Much love. Catch y'all in a couple days.